Hi everyone, welcome to another stunning session. We are a team of passionate developers where we keen on learning about new tech stacks. We don't rely on the current one, so we keep on learning. So, as we are aware that we are getting a new tech stack in our list, which is again ZIO, which is just like a module of akka. So there is a number of things to learn about, but as I said that we are the developers who keep on learning new things. So we are back with then another new session which is all about introduction to the ZIO Fibers. So I hope we will be learning a number of things, means what actually are the key features, and why we should learn that. So I welcome Pragati Dubey, software consultant in Noldes INC, and before the session gets started, I encourage everyone, if you do have any doubt, please raise your voice, means keep on asking us. We are good, we will be good to help you, to answer you. And also one thing which before the session starts I would like to add is Pragati Dubey is writing a number of blogs, and I feel very proud to say that her blogs is being recognized by the Scala communities and has been mentioned in the Scala Times as well. So again, I encourage everyone, if you do have any doubt, please ask us. So I welcome Pragati. Pragati, the session is all yours. The stage is all yours. Please start the session.
Thank you. Thank you so much, Kuldeepak. So, hello everyone. Good evening. My name is Pragati Dubey and I'm working as a software consultant in Noldes. Today, I will be delivering a knowledge session on introduction to ZIO Fibers. So, let's go to the slide share. I hope everyone can see my screen.
Yes, it's visible, Pragati.
Yes. So, before moving forward, let's take a look at the knowledge etiquettes. So first one is punctuality. We must all join the session 5 minutes prior to the session start time, as when we start on time, we conclude on time. Silent mode. We must all keep our mobile devices in silent mode and feel free to move out in case of any emergency or a call. Feedback. Make sure to submit a constructive feedback for all the sessions. It is very helpful for the presenters to improve themselves. Avoid disturbance. Please keep yourself on mute and try to avoid any unwanted chit chat during the session, but you're always welcome for any kind of questions or queries. Now let's move on and take a look at the today's agenda. So today we will be learning about introduction to ZIO Fibers, how ZIO Fibers are different from operating system threads, key features of ZIO Fibers, followed by basic operations on ZIO Fibers and a quick demo. So moving ahead. So some of you might be like joining the session for the first time and might not be aware of the ZIO library. So for those people, I am going to give you a quick overview of ZIO library first, and then we'll go ahead with ZIO Fibers. So ZIO is a concurrent programming library which uses Scala programming language capabilities to help us design efficient, resilient, and concurrent applications that are simple to understand, test, and do not leak resources, cause deadlock, or cause errors. The Z in Scala Z, the SCAD in ZIO came from Scala Z, and also the IO came from IO monad. Okay. ZIO is a next generation framework for building cloud native applications on the JVM with a beginner friendly yet powerful functional core. ZIO is built around a powerful data type called ZIO itself, which serves as the foundation for any ZIO application. So basically, ZIO library is purely functional library and showcases power of pure functional programming to solve modern business problems. Okay, moving ahead. Let me tell you just some of the features of ZIO, and then we'll move ahead with ZIO Fibers. Okay. So ZIO Fibers, ZIO has some of the features like concurrency, which we will see today, efficiency, error handling, and resource safety, streaming, along with testability. Quick intro about ZIO data types. So ZIO as I told you, like all the data types are derived in ZIO from the ZIO data type itself. So they mainly contain 5 data types, that is UIO, URIO, task, RIO, and IO. And all of those data types contain mainly 3 elements, that is R, the environment type, E, the error type, A, the success type. And I guess you might all be like a bit know about all those types. So in the E, we map the errors. A is the success type of the value, and R is the environment that is like new to us. So yeah, moving ahead. Uh, Before we go ahead with ZIO fibers, we must know what ZIO effects are. Okay, so just a quick brief on that. A functional effect is a template for a concurrent workflow. The template, which is mostly descriptive in nature, used to test any kind of side effects such as database interaction, logging, streaming across the network, or request approval. We can convert any procedural program into ZIO by wrapping each statement in a constructor such as ZIO effect, and then binding the statements together with flat map of all comprehensions, or maybe just chaining them together. So that was a quick intro about ZIO effects. Now we shall move on to ZIO fibers. So fibers are lightweight equivalents of operating system threads. They enable tremendous scalability compared to threads and are reinforced with resource safe cancellation. Like a thread, a fiber models a running computation, and instructions on a single fiber are executed sequentially. We will look at this particular statement later part of the demo. Okay, let's see how fibers work, and to understand that we need to learn a bit about ZIO runtime and how it executes our programs. Okay, so when we call unsafe run in the ZIO runtime, the ZIO runtime creates a new fiber to execute our program. A fiber represents a running program that we happen to not have started yet, but will be starting at some point of time. You can think of it as a thread we have created to run our program logic, but have not started yet. The ZIO runtime will then submit a fiber for execution on some executor. An executor is typically backed by a thread pool in multi-threaded environments. The executor will then begin executing the ZIO program one instruction at a time on an underlying operating system thread, assuming one thread is available. So yeah, this executor portion is similar to that of like having a future, and it has an execution context that manages all the threads. So it's kind of a same thing for that comes from the Scala itself. So that was a quick brief about ZIO runtime and how we execute a fiber. Now let's move ahead and come to the second part of the agenda, that is ZIO fibers versus threads, or maybe how fibers are different from threads. So let's start with the similarities between ZIO fibers and operating system threads. So ZIO fibers, just like operating system threads, have well-defined lifespan, that is dictated by a effect that are executing. Fibers also contain distinct identities, stack traces, local state, and statuses like done, running, or suspended. Every fiber fails or succeeds depending on the effect that it is executing. Okay, so mainly every fiber executes an effect, and it depends. Its execution or its success or failure depends on that particular effect. Okay. But then what makes a fiber different from threads? Like if they are so similar, then why do we need fibers, right? So threads have some of the limitations, and now we look into those parts. Threads are generally scarce. Threads on the JVM map to the operating system level threads, which impose an upper bound on the number of threads that we can have in our application. Moving on to the next one, that is, threads are expensive on creation. Creation of threads is expensive in terms of time and memory complexity. So yeah, we will see it later, like how we can overcome these problems. moving on to the next one. Threads have much overhead on context switching. So context between the execution of one thread to another thread is not at all cheap. It costs us a lot of time. Now the last one, that is lack of composability. Now what is it? So basically threads are not tight. That means they don't have a meaningful return time. In Java, create a thread and we have to provide a run function that returns a void. And it is similar to the unit type that we have in Scala. So thread cannot finish without a specific value. And due to this limitation, we cannot compose or mix them together. Also, a thread has no type parameter for error. Hence, an ideal thread is expected to throw any exception of type throwable to signal errors. But it does not do like that. So it is one of the limitations of thread. Okay. So here we looked into some of the similarities of the threads with some of the limitations that threads have, and maybe like we can look into further like how fibers can overcome some of them or maybe all of them. Moving ahead.
Pragati, your voice is breaking in between.
Features of ZIO Fibers. So now let's take a look at features of ZIO Fibers and try to comprehend how fibers can own the relations of threads. We have found the first feature, sound size. Okay. Let me try to switch my
Pragati, you have some issue in the network.
am I audible now?
Yes, you are audible.
Okay, okay. I guess I had some network issue. Is my screen visible or like
Yes,
should I
yes, it
reshare?
is visible. Can you please repeat the last slide?
Yeah, going ahead. Can you just tell me which one? So
Yes,
till where were
this
we?
one. Yeah, right.
Okay. Have we gone through the similarities or not, or maybe just the differences where we broke? Like,
You were explaining the differences.
okay, okay, okay. So let me quickly go through the differences again. Yeah. So basically, there are some limitations of threads, and that might be overcome by fibers later part in the later part that we will look at that later. So yeah, threads are scarce. The first thing is that threads are scarce, and why they are scarce is the threads on the JVM map to the operating system level threads, which impose an upper bound on the number of threads that we can have in our application. So in that way, maybe threads are scarce and we cannot have a plenty of them, and managing them will also be one of the criterias that we need to think of. Okay. So next one is expensive on creation. The creation of threads is expensive in terms of time and memory complexity. So they actually take a lot of time and memory complexity. Yeah, obviously they offer us scalability and all, but yeah, it is quite expensive. So much overhead on context switching. So context switching between the execution of one thread to another thread is not at all cheap. It costs us a lot of time. And yeah, in case of like primitive scheduling, when there are multiple threads, we want like one thread is executing and then going back to the runnable state, and then again another thread comes to the running state. In that kind of a scenario, the overhead is too much. So yeah, that is one of the limitations of threads. Moving on to the last one, that is lack of composability. That is, threads are not typed. That means they don't have a meaningful return type. We create a thread and we have to provide a run function that returns void in case of Java, and it is similar to the unit type that we have in Scala. Okay, so threads generally cannot finish with a specific value, right? And but like in case of Scala, we all know we all work on specific values that function returns, or maybe the return type. So threads don't have it. Due to this limitation, we cannot compose threads. Also, a thread has no type parameter for error. This, like an ideal thread, is expected to throw any exception of type throwable to signal errors. Okay, but since it does not contain any such parameter, so it poses as a limitation for us. So now let's look on to the other part and see if fibers can overcome all these limitations in some or the other way, and maybe just help us out through this situation. Okay, so here I've come to the features of ZIO Fibers, and let's see if some of the features can overcome the limitations of the threads. So the first feature is unbounded size. The mapping of JVM threads to operating system threads is 1-to-1, but the mapping of fibers to threads is many to one. So basically, plenty of fibers run on a single thread. So yeah, obviously increase scalability, and each JVM thread will end up expecting or executing each JVM thread will end up executing anywhere number of hundreds to thousands of fibers on a single thread, or maybe concurrently also, by hopping back and forth between them as necessary. This gives us virtual threads have the benefits. This gives us the benefit that virtual threads have the capability of like a high scalability over threads. Maybe I should say that fibers are called as virtual threads. Okay. In other words, fibers offer us massive concurrent lightweight green threading on the JVM. So fibers basically help us in order to do green threading. Second feature is lightweight. So just now we saw that creating a thread is quite expensive, and in comparison to that, fibers are like virtual, and they help us in green threading. So they are considered as lightweight cooperative threads. This means that fibers always yield their execution to other without the overhead of primitive scheduling. So just now I told you about what is primitive scheduling. When the threads or the fibers are trying to like go from the runnable state to the running state, and again going back in order to like complete the job as fast as possible. So in that case also, a fiber always yields their execution to another fiber. Now the next feature is asynchronous. Fibers are asynchronous while threads are synchronous. That is why we scale better than threads. So basically, it is a feature which helps us in scalability. Now here comes an important feature, that is typed and composable. Fiber data type is mostly similar to Scala's future data type, which represents handling a running asynchronous computation. Fibers have meaningful return type and allow us to write more type-safe programs. That is, fiber has an error type and a success type. Okay, so the error type E contains or maybe suggests that a fiber may fail with this kind of a value. And the success type helps us in telling that the fiber may succeed with this kind of a value. A fiber does not have the environment type. As we all know that ZIO generally contains three types, that is R, E and A, but the fiber does not contain the R type because Fibers only execute effects that already have the requirements provided to them. So the fiber does not need an environment type, as it is just executing the effect, and that effect contains its requirements. That effect already contains its type R. Okay, moving ahead. That is, next part is structured concurrency. This is one of the important features of ZIO Fibers. ZIO provides structured concurrency, and it works like all the child fibers are scoped to their parent fibers. That is, when the parent effect finishes execution, all the child effects will also automatically be interrupted. So when we fork, we get back the fiber. A fiber's lifetime is bound to its parent fiber that forked it. And it's almost impossible to leak fibers because child fibers are guaranteed to complete before their parents. So basically, this is one of the way I told you, right? We can have plenty of fibers and they can be mapped to one thread, like they have a many to one relationship. And this is a way to like manage those fibers in a better way possible. The structured concurrency. The structured concurrency gives us a way to reason about fibers' lifespans, which we can statically reason about the lifespan of the children fiber just by looking at our specific code. We don't need to insert complicated logic to keep track of all the child fibers or manually shut them down. As if a parent fiber terminates, the child fibers will also terminate. Okay. It also contains concepts like global lifetime and fine grain scope. So a global lifetime is when, in some case, we want a child fiber to outlive its parent fiber. And in that case, there comes the concept of global lifetime, and that can be handled by maybe a function named as fork daemon. So all that will not be covered in this session, maybe in some other session. But yeah, structured concurrency contains all those portions. Minimizing the fiber scope, that is the second point. What if we want to like we don't want to just keep it running until its parents time span is over or the lifespan is over? We just want a fiber for very short span of time. So for that, we have a function like forkin, which will also be covered in some further sessions. Okay. So in all, compared to operating system threads, ZIO fibers consume almost no memory, have dynamic stacks that grow and shrink, don't waste operating system threads without blocking operations, with blocking operations, and can be safely interrupted at any point in time. Also are strongly typed. Just like I told you, fiber has a success and a failure type. Moving on to some basic operations on fibers. Okay, so some basic operations are forking effects. So here, like I have mentioned, forking effects, basically when we fork an effect, we start a fiber. So the most fundamental way of creating a fiber is to take an existing effect and fork it. And conceptually, forking an effect begins executing the effect on a new fiber. Okay, giving you the reference of the newly created fiber. Thus, whenever we need to start a fiber, we have to fork an effect and get a new fiber. Okay. But yeah, now the question comes, what if we don't fork an effect? Will the execution will not be running on any fiber? Whenever we run any program, likewise, in generally, then it runs on the main thread, right? So similarly in ZIO, if we run any program, it runs on the like a single fiber or the main fiber, I would say. Okay. Now, the next point is joining fiber. Joining is the way of waiting for that fiber to compute its value. That means we are going to wait until it's done and receive its result. The effect returned by the fiber.join will succeed or fail as per the fiber. So it is similar to like chaining effects or that we do in Scala generally. Moving ahead. That is awaiting fibers. To inspect whether a fiber succeed or failed, we can call await on that fiber. This is basically a bit different than joining. This call will wait for that fiber to terminate and give us back the fiber's value as an exit. That exit value could be a failure or a success. Last one, that is interrupting fibers. A fibers whose result is no longer needed may be interrupted, which immediately terminates the fiber. The interrupt operation does not resume until the fiber has completed or has been interrupted and all its finalizers have been run. So these were like some of the basic operations or the very basic operations on fibers. There are plenty more that we can cover in some of the following sessions. But yeah, like just we saw that what are the key features of fibers, ZIO fibers, and some of the weight like to how we can start a fiber by like forking it and everything. We can see it in the next part. So now I will take you to the demo portion. So firstly, when we see like how we run the effect normally. So let me show you here. Here I've tried to create like 3 effects. Its type is UIO, and that means that this effect will always succeed with this value. Am I correct? So yeah, this one here I've tried to create a print thread, and this is basically trying to print the name of the current thread or that on which I'm running it. Okay, and here you can see that I have not forked any kind of a used any kind of a function like fork or anything like that. I'm not forking anything. So now just let's see, let's just run and see like what kind of result I'll get. Okay, so here you can see that all these effects succeeded. Okay, and all of them ran on the same fiber. Okay, so what I explained you some time back was like even if we don't fork any fiber, is there not any fiber? There is. Okay, so all these effects ran on the main fiber, that I would say. So this was the synchronous computation that like ran one after another and ran on the same thread or the same fiber, I would say. Like you know that plenty of fibers are mapped to a single thread. Moving to the second part. Okay, so here again I have created some of the tasks. Again, they will be succeeding with these kind of values like task 1, task 2, and task 3. And yeah, but here, as you can see, the difference from that part is I have forked each of the effects. Okay, now forking effect, as we know, this will run the computation on a different thread. Okay, just like we have it in Scala, when we like construct a future value, then it runs the computation on a different thread. So it is quite similar to that. Now let me try to run it. Yeah. So as you can see, earlier when we saw it, all of the tasks ran on the same thread, but here as we can see, they all ran on the different threads. If I try to run it again, you can see the right now the order is the second task ran on thread 3, task 3 ran on thread 4, and task 1 ran on thread 2. If I rerun it, you can see the order is changed. So every time I rerun it, the order will be changed as and when it gets resources and it is like taking them and then executing these tasks, basic tasks on different fibers, or I should say threads. Okay, moving ahead. So this was one of the ways how we can maybe just fork an effect, very basic effect, and start a fiber. So it's not that complicated, right? We have just changed them and try to yield a value. Yeah. So next part would be. So yeah, again I've constructed 3 tasks, quite similar. Yeah. Here I've tried to like join the asynchronous fiber as the function name suggests. So I have taken task 1. I've tried to fork it. That means running it on the different fiber. Again, I've for task 2, so this will again run on a different fiber. And here comes another thing, that is zip. So let me drill you through that and tell you what is it. I guess we must all know that it combines two fibers. Okay, so yeah, so zip method combines two fibers into a single fiber that produces both results. So it is like a similar function that we have in Scala, and we use it in for zipping things. So yeah, it is a similar thing. And also you can see it here. Here I've used another function named as joined. So let's look into it. Joins a fiber. So basically this function joins a fiber which suspends joining fiber until the result of the fiber has been determined. Attempting to join a fiber that has errored will result in a cacheable error. Quite simple. Joining an interrupted fiber will result in an inner interruption of this fiber. Unlike interruption triggered by another fiber, inner interruption can be caught and recovered. So this was a quick overview of about join. So when we try to like chain different fibers, then we can use join, as we don't want to like, when we don't want the computation to end just like that, if we will not join it, the computation might end then and there. But if we want that the computation should wait for another fiber to complete, or the another effect to complete its computation on the different fiber, then we need to join them. So let me just try to like run this and show you the output. Okay, so as you can see, like task 1 ran, task 2 ran, these all ran on the different effects. This was the result of zipping them together. I'm sorry for the background noise. Yeah, so this was the ran when we tried to zip them together, or maybe zip the results of both of them together, and it ran, and you can see it also ran on a different fiber, right? And again, when we tried to join them, it waited for computing all the results, and then this one is displayed. So none of them like ended abruptly, right? So here you can see task 1 and 2 are working asynchronously, whereas task 3 is waiting for them to complete. Okay, so task 3 waited for them to complete as we are trying to like zip them. So it can so that it can zip these two tasks together and result in this part. And then the final task 3 joined and printed the result of the task, the fourth task, or I would say the last task. Okay, so yes, this is like a quick overview about like when we want to zip them together, zip fibers together, and joining them together. Okay, now let's come to the last operation, or maybe last operation of this session. So that is awaiting a fiber. So yeah, here I've tried to let's just drill in and see what await does. So awaits the fiber, so which suspends the awaiting fiber until the result of the fiber has been determined. So basically it we can just think of at like await dot result or something like that, that we have in Scala or maybe futures. So what it does as basically when we try to or want to know if the fiber succeeded or failed with the current value, then we use this function, and this tells us that the effect, maybe just everything about the effect, that it succeeded or failed with that current value. So yeah, definitely it is different from joining, as joining is like when we want to join two fibers together, we want like it is similar to chaining, but here we just want to want the value of that fiber if it succeeded or failed. So this is kind of a basic difference between await and join. Yeah, so let me just run it for you and show you what the result is. Okay, so it just got executed, and after executed we just gave the awaited fiber to the exit, and it yielded that value, right? So here it says awaited fiber sends hi. So this was a quick brief about some basic operations on fibers, like how we can create a fiber by forking them. What if we don't like fork any fiber, then what is that situation, and how the effects are running if we have multiple effects, so they run synchronously. What if we like try to run all the effects and like try to fork all the effects, and will it maybe run on the same fiber or the different fibers. So as we saw, like they run on different fibers when we try to fork them. Also, we saw like how we can join them together, how we can zip them together, and what happens when we try to await the result. So going back to the deck again. So this was a quick demo about the basic operations on fiber data types, or fibers, I would say, ZIO Fibers. So that was all for my session. Am I audible?
Yes, you're audible, Pragati.
Yeah. So yeah, that was all about ZIO Fibers. That was a quick introduction about ZIO Fibers. That might be continued with some other sessions that will explore or dive deep into ZIO Fibers. It was a quick and like basic session about ZIO's fibers. Yeah. So that was all. Thank you. Thank you, everyone.
So thanks, Pragati, for this wonderful session.
Thank you.
I encourage everyone, if you do have any question, please ask Pragati. We will be good to hear you and will happy to answer you. And I would like to thanks Pragati for this wonderful session. And what are the key points for me to take away from here means what actually are the ZIO fibers, how they are different from threads, the key features, operation, ultimately the demo you should help me in understanding how to work with that. So thanks Pragati. And if anyone do have any feedback or any questions, please come up and speak. I encourage you.
Thank you. Thank you so much, Kuldeepak, for the feedback.
It is a really nice session. Thanks, Pragati.
Thank you. Thank you, Pallav.